Well, welcome to Lecture 11 in Topology on connectedness. This is section 4.1 in Minetti, and I'll start with his definition. Here we go. A topological space is called connected if the only subsets that are both open and closed are the empty set and the entire space. And furthermore, if X is not connected, then it's said to be disconnected. All right. Now, I don't think this was the definition that was given in my topology course. I think when I had topology, and I think we used Moncrief's, and I don't know, that may or may not be the definition of Moncrief's. I haven't double checked, you know. But a lot of times people define connected in terms of separation. So a space is said to be connected if there does not exist a separation of the space. What's a separation? A separation is a pair of, I'm missing a word there. It's kind of important. Non-empty. Non-empty. Open non-empty sets U and V such that they're unions, the whole space, and such that they are disjoint. So if you can do that, you've separated the space. All right. And this is equivalent to the definition above. See, because if you had the whole space as the union of U and V, if you think about it, if they're both open, that means the complement of U is V, and if V is open, that means U is closed, and vice versa. See, if the complement of V is U, and U is open, then V is closed. So if these are both open, then they're both open and closed, all right? And and the condition that they're non-empty means that they're, you know, that there's more than just, you know, the empty set in the whole space in this discussion. So first up, we come to a lemma, and here is the lemma. Scooch it up a bit here. I got some coffee today, and I didn't realize it, but we're out of milk, and so I'm put this almond coconut stuff in my coffee, and it's just not doing it. It's just not right. But I gotta drink it, so I'm gonna drink it. But I'm not gonna like it. Anyway, so lemma 1. Topological space X. The following are equivalent. X is disconnected. X is the disjoint union of two open proper subsets. That was pretty much my discussion up here. And X is the disjoint union of two closed proper subsets. So implication of 1 implies 2. So suppose X is not connected, and suppose that A is a subset of X open and closed and non-empty, and furthermore suppose that A is not equal to the empty set or the whole space. All right, well, if that's the case, then X minus A, the complement of A, is open. And if we set B equal to the complement of A, then we find that A and B are open with X as the union of, you know, both of these. And their intersection is empty, and hence 2 is true. See that? Because X is now, it's the disjoint union of two open proper subsets. So we assume not connected, we got X is the union of two open proper subsets. So that's 1 implies 2. And then, of course, while you're at it, you might notice that X minus B is the complement of A, which is A again. So that's open, which means that B is closed. So that then means that A and B are both open and closed. And so we also have that X is the disjoint union of two closed proper subsets. And to get 2 implies 1, if you assume that X is, make sure I'm on the page here. If we have X as the union of A1 and A2, where they're non-empty and they're open and the intersection is trivial, then you have that the complement of A2, which is A1, is both open and closed. And so that's, in our Minetti way of thinking, that proves that X is disconnected because you've got a proper subset which is both open and closed. All right, so yeah. You have a non-empty proper subset which is both open and closed. That proves it's disconnected. Okay, so going forward, I will prove connectedness or disconnectedness using this lemma, probably without thinking. So, like my default, like I said, I was taught this is the definition of connected. So I tend to default to that if I'm not thinking about it. All right. Although there are important places, certainly in applications. Like one of the, there are some proofs in, for example, complex analysis, which use this definition of connected. Like there's a place in complex analysis you prove that a set is both open and closed, and in so doing, you prove that it's the whole thing because it's like the. Let's see, I'm trying to remember the set is connected for some reason. You prove that that set is both open and closed, and then that proves that. Well, I'm butchering it, but there's a place where the definition of topology connectedness is used in the complex course. I remember it. I wish I could remember what it was. It was I can't quite remember which proof it was, but it's in there. Anyway, sorry, I'll try to make more useful comments for the remainder of the video. It's anybody's guess what'll happen. So example 1, you can look at the space as being the real line with 0 deleted. Okay, that's a topological space. Then you notice that these subsets, minus infinity, like the negative numbers and the positive numbers, they intersect at the empty set. They're both open in the subspace topology of X, and they're complementary, right? Which means that they're both open and closed. So you have two sets, two proper subsets. They're both open and closed, and their union is the whole space. That means that this is a disconnected space. Okay. So next up here, lemma 2. And I think Minetti has like a sentence for the proof here. And who knows, maybe his sentence is more clear than my proof. That's possible, I suppose, but I try to be stupidly pedantic here. We'll see if I succeeded. I think odds are good for it, given the length of my proof. So let X be a topological space. A subset of X is open and closed subset, okay? Then for any connected subspace Y, either Y is a subset of A, or Y intersects A, Y intersect A is empty. So here's kind of like a picture of the idea of what's going on. We've got the whole space, we've got A, which is an open and closed subset, all right? And then we've got a subspace Y, right? Y is a subspace of X, so there's different things that could happen in principle. Of course, one thing that could happen would be A surrounds Y, not in my picture, right? And also that the intersection of A and Y is empty, also not my picture, right? So my picture illustrates these things not happening, right? For what it's worth. Okay, so let's go on here. So here's the proof. Suppose A subset of X, is both open and closed, and also suppose that Y is a connected subspace. Then, of course, we have that both A and the complement of A are open, all right? And they're also complementary, which means that they're also both, well, they're both open and closed, okay? So, because if A is open and closed, its complement is open and closed, is the bottom line here. You should make that like a lemma on like day 2 of topology. If a set is both open and closed, its complement is both open and closed. That would have been I should have put that problem on your test. Why didn't I do that? Man. Oh, sorry, I haven't graded your test yet. I'm thinking about it. I'm thinking about doing it. Today, maybe today. All right, my apologies. All right, so you're like, I don't want your apologies. I just want you to grade the test. Fair enough. Fair enough. Observe that y is the union of everything in y that's not in A and everything in y that's in A. That's this set and that set, right? So we can write y as the union of this and that. But it's also pretty clear that these are disjoint, right? Disjoint subsets of y. And it's also clear that if we complement y by the complement of A, the complement of A inside y, complemented inside y, is just the part of A which is inside y again, all right? And if we complement the inner, the part of y which is in A, it's everything that's not, it's everything in y that is not in A. That's the complement of this, all right? So what I'm saying is that y minus A and y intersect A are complementary sets inside y. I'm just saying what I wrote here anyway. Okay, fine. If y is a subset of A, all right, so we're trying to prove either y is a subset of A or that, right? So this sentence here isn't really needed, technically speaking, from a logical perspective. Like, this isn't really needed. We could just jump it past the anyway. But let me just talk about it for a second. Suppose y is a subset of A. That's okay, because if y is a subset of A, then y intersect A is y, and so y minus A is empty. So, but anyway, the larger, okay, I'm just making a comment here. That's what happens in that case. But the point is, if y is a subset of A, well then, okay, the lemma's true, right? So what remains to see then is that it either has to be this or that, right? So to prove that, I could look, let's see here. So I say, suppose y is not a subset of A, and that y intersect A is empty. So if these things were both true, that this lemma would be, the claim would be false, right? So I'm working on a contradiction here, okay? So suppose y is not a subset of A, and I'm sorry, let me try to keep it in the frame here. Can we see my bottom of the page? Just a second, I understand. Oh, yeah, we're fine. Okay, so suppose y is not a subset of A, and the intersection of y and A is not empty, rather. Then y minus A is also not empty, and as I just said, y intersect A is not empty yet. So you have, in other words, these are two non-empty sets inside y whose union is all of y, and hey, they're both open. That means that we have a separation of y by these sets. Oh, but that's a contradiction because y is connected, all right? So you cannot have both y is not a subset of A and y intersect A is empty, which means that if y is not a subset of A, it must be that y intersect A is empty, among other things. Okay, hence, if y is not a subset of A, we must have that y intersect A is empty. All right. So I guess the other thing I was worrying about is, how do I know that y minus A is open in y? Well, the details are down here. Y minus A is open because y minus A is the intersection of the complement of x by A with y. And so in the subspace topology, this is open if it's the intersection of a open set in the superspace with the subspace in question, in this case y. So there you have it. So there's lemma 2, and a unnecessarily detailed proof of it. Okay, so there you go. Don't worry, my proofs will get less detailed as this lecture goes on. Guarantee it. Page 3. So this is one of those examples in Minetti that's really kind of more of a proposition. It's a proposition masquerading as an example. I'm not sure this is really an example. So sometimes I feel like people say, well, I want to have so many examples in my book. I know, I'll just change this proposition to an example. Then I've got another example, right? I don't know. It doesn't feel like an example to me. It feels like a theorem or something. Let X be a topological space, K a closed subset, U an open subset which contains the closed subset, if X and the complement of u by k are connected, then we also have that x, the complement of x by k is connected. I made a picture to try to get the idea of it. So like I'm thinking about it like I've got my whole space X, I've got this open subset U, right? I've got some closed subset I've called K, right? And we're given that, what are we given? We're given that X and X is connected, all right, and U minus K. So U minus K would be like everything outside of the green triangle and inside the red dotted oval here. So you're given that X and the, in between of the K and the U are connected, and then likewise X minus K is connected. So, I mean, once you draw the picture and you think about it for a second, it seems like, oh, okay, that seems reasonable, but let's prove it. All right, so, still coconut almond. Still coconut almond. Gah. No. Yeah. Yeah. Sorry. I need to finish it though. I'm not a quitter. So suppose towards a contradiction that x minus k is disconnected. In particular, suppose that it has a separation by a and b. All right? They're open and closed. Okay? Then since they're both open and closed in x minus k, I can apply lemma 2. Let's think about that. Well, what was lemma 2? So soon I forget. That's the trouble with making a proof too long, is you forget the lemma. All right. Only partly joking. So this was lemma 2. It gives us that if we have an open and closed subspace and a connected subspace, then either the open and closed subset contains the subspace or it intersects it trivially. So, oops, okay. By the way, it's very sad, but one of my, look at this, see what happened? I lost the end of it. So sad. And now I need new chopsticks. But I guess it still works though. Anyway, so A intersect B is empty. Alright, so great. We have A and B open and non-empty, and since U minus K is assumed to be connected, and it's a subset of X minus K, then by lemma, so we got this is playing the role of Y, right? This is playing the role of Y in the lemma 2. We find by lemma 2 either U minus K is a subset of A, or U minus K has to be a subset of B, all right? I guess maybe we're applying lemma 2 twice, maybe, in some sense. Oh, God, I gotta get some candy or something. All right, anyway. Okay, going on. So without loss of generality, suppose that it's a subset of A, all right? I mean, A and B appear symmetrically here, so it should, if we can make the argument for A, we can make it for B. So if we have that A, if it's a subset of A, that means that U minus K intersect B must be empty. Remember, because otherwise that would mean that A and B were not disjoint. Yeah. Because they would have something in common. If this were non-empty, then that would give you something that was common to both U minus K and B, and hence it would also be an A, which would be trouble because A intersect B is assumed to be empty. All right, moving on here. Then A union K is equal to A union U. Let's see here. So if I take the union of A with K, all right, it should be the same as if I take the union of A with U. I think that makes sense because of this right here. And of course, the intersection of U with B is empty. If there was something in U that was also in B, right, then that would make this non-empty unless unless you somehow had it so that it was in it was in, how can I say this? I think we're also using this U minus K as a subset of B for that. All right, anyway, so getting on here. So what we have is that X is A union K union B, but it's also A union U union B. Okay, because this is equal to that. But then you have that X is the union of two open and disjoint sets, which says that X is disconnected. But that's bad because we assumed that X was connected. So there you go, contradiction. Woohoo! Therefore, since we have proved that, supposing that X minus K is disconnected implies a contradiction, that implies, of course, by proof by contradiction, that X is not disconnected, which is to say that X minus K is connected. All right, moving on. Yeah, come on. All right, here we go. Next up, and this, I think, is by far the most fuzzy thing in this lecture. I don't entirely understand. Well, maybe I'll understand it when I talk about it here just now. Let's see what happens. Sometimes when I talk about these proofs to you guys, somehow something magical happens, and I understand it as I'm reading it. But I think that this is partly based on some real analysis that we haven't proved. So anyway, the interval 0 to 1 is connected in the Euclidean topology. That seems totally obvious, right? But how do you prove it? Well, he proves it by Minetti. This is Minetti's proof, of course. Credit where credit's due. And I'm not saying that the proof is not clear. I'm just saying that maybe I don't understand it. So those don't have to be the same thing at all, yeah? So suppose C and D are non-empty. Well, they're non-empty, closed subspaces of 0, 1, right? So we need to show, to prove that this is connected, we need to show that it's a necessary consequence that these are intersecting, right? If these closed subspaces were non-empty and they intersected at no point, then that would be a violation of 0, 1 being, I mean, that would prove 0, 1 is disconnected. All right, so let's see why that does not happen. And so we're going to take a pair of closed subspaces of 0, 1 whose union is the whole space. Now, if the union of C and D is the whole space, either zeros in one of them or the other of them. So without loss of generality, we can suppose zeros in C, right? Because, again, C and D appear completely symmetrically up to this point. But now we're going to assume zeros in C. I've broken the symmetry. All right. And we're going to let D be the infimum, also known as the greatest lower bound, right, of D. And I think you can couch that in terms of taking all possible sequences in D and looking at the greatest lower bound of all possible sequences taken from D or something like that. Anyway, this much we can say. If we have a subset of real numbers, right, and that subset of real numbers is bounded below, right, it will have a greatest lower bound. This is an axiom of the real number system. Or it's a close cousin to the greatest upper bound axiom. If you have, I mean, it is true, if you have the axiom that there exists a greatest, a supremum for every set that's bounded above has a least upper bound, so there's a lub. If that's the case, then you can use that to prove the existence of a greatest lower bound through some kind of like negative switcheroo argument. But anyway, the point is it is either an axiom or very close to an axiom that if you have a set of real numbers which is bounded below, it will have a greatest lower bound. And is D bounded below? Well, D, big D, is a subset of 0, 1, right? So definitely 0 is a lower bound for D, so yeah, definitely this exists, all right? You're like, well, my real analysis course, we defined real numbers in terms of Dedekind cuts, so it wasn't an axiom for us, and to that I say, go away. Okay, so, well, then you proved that, at some point in your real analysis course, you proved that if a set is bounded below, there exists an infimum for the set. That happened. All right, fine. So we seek to show, seems like I'm whistling here, we seek to show that D is an element of this infimum of the set D. We're going to show that that little d is an element of the intersection. Okay, so from real analysis, D is an element of D since D is closed. How do I know that? So, excuse me. So you can define it as, I think you can, there's some results about subsequences and stuff that you can look at for the infimum, and then if you have a closed set, then every sequence that you can possibly take in a closed set, the limit point of that sequence, I should say it more carefully, every convergent sequence in a closed set must converge to a limit point inside that set. So essentially you can look at D as like a limit point of various sequences. Well, anyway, however you want to say it, little d has to be an element of big D because D is a closed set, which implies like sequentially closed. And if we had all of the bells and whistles of real analysis, then we'd have this pinned down for sure. Okay, my apologies, I'm a little bit fuzzy on the order of operations for reals. I haven't taught it, My bad. It's been a while since I took it, and I'd like to think I've learned something since I took that course. But that's different than teaching the course, yes. Anyway, so if D is equal to 0, well, if D is equal to 0, then we're done, because 0 was an element of C by assumption. If 0 is an element of D also, then the intersection has 0 in it, and that shows that that C and D are not disjoint. Yep. So if D is not 0, it must be positive, because D is taken from 0 to 1. And if we consider the set E, which is the intersection of C with the closed interval from 0 to D, all right, well, you've got the intersection of two closed sets, which again is closed, right, as we know from topology. And Euclidean topology is, after all, a topology, so there you go. So this is a closed set, and it's a closed set which is a subset of, well, let me say it this way, the Klopen interval, 0 to D not included, is a subset of E, right? And since E is closed, we look at the closure, you know how closure works, right? The closure of a subset is a subset of the closure of the superset, but since the superset is closed, it's equal to its closure, which shows you that the closure of 0D is a subset of E, which is to say that, what is the closure of 0 to D? Well, in the Euclidean topology, that's just straight up. Here, I'll add something here. To be clear, this is equal to 0 to D, D included, right? So that's equal to the closure, the Klopen set, closed open, of that. In the Euclidean topology, that's equal to that, right? So, lo and behold, that gives us that D is an element of E, right? So therefore, D is an element of E. And if D is an element of E, that means, and E is formed from this intersection, that means that D is also an element of C, which means D is both in C and in D. And hooray, that means that the intersection is non-empty, which shows that there does not exist a disjoint. You can't find a pair of disjoint closed sets whose union is the whole interval from 0 to 1, and also you have trivial intersections. You can't do it. Wouldn't be prudent. And so I got through this proof, and then I was like, This is so hard. There must be another way. And then I thought, oh, I remember path connected implies connected. So here's the proof that 0, 1 is path connected. Okay. So I guess I'm putting the cart before the horse here, admittedly, because we haven't defined path connected yet. But just, bear with me here. Here's a fun alternate proof. So let A and B be elements of 0, 1, then we can construct gamma of t, a plus b minus a times t. All right, this is a path. It starts, put t equal to 0, you get a. Put t equals to 1, you get b. It's clearly a continuous path. And it starts at a and it ends at b. It's inside the interval 0 to 1. So therefore, since a and b were arbitrary, we see that 0, 1 is path connected, and hence connected. Hooray! And that seems like a really easy proof, doesn't it? You know something? Anytime in mathematics you feel like, man, my teacher works so hard, but we know later something easy, something, and we know something later and we can just prove it so easy. Why didn't we just do that, There's probably a reason for it. So let's stay tuned for the reason. Something funny happened. So all right, here we go. Next up, we'll come back to my proof too. There's a reason that's not a good proof. Okay. Let F be a continuous map on topological spaces from one topological space to another. If X is connected, its image is connected. So in other words, to summarize this theorem, the continuous image of a connected space is connected. So suppose you've got a connected map, you have a continuous map, suppose X is connected. Let V be a subset of the image of X under F, and let it be both open and closed in the image. Then by definition of subspace topology, for f of x a subspace of y, there exists a open A in y, open A subset of y, and closed C a subset of y, for which V is the intersection both of the image with A and the image with C. This is what it means for V to be open. This is what it means for V to be closed in the subspace topology, namely that you can intersect the image, f of x, with a respective open or closed set in the superspace Y. So like that's what the subspace topology of the range is defined to be. It's open if it intersects with an open space, open set from the larger space. It's closed in the subspace f of x if it is formed by the intersection of a closed set with the larger space, in this case y. But since f is continuous, we know that the inverse image of V is the same as the inverse image. Think about this for a second. It's not that hard to see why this is true if you have what's above. F inverse of V is equal to F inverse of A, but it's also, by this equation, equal to F inverse of C. But the inverse image of open is open, and the inverse image of closed is closed, which means that the inverse image of V is both open and closed. It's an open and closed, but the image of V is both open and closed in X, but X is connected, which then means that the inverse image of V, so we've got a subset of inverse image of V is a subset of X, which is both open and closed. X is a connected set. F inverse of V, by the way, is non-empty. That leaves us with only one possibility. F inverse of V must be the whole space. So F inverse of V is equal to X, which is to say that V is equal to F of X. All right. So anyway, then that shows you that F of X is connected because we took a subset of it that was open and closed, and we were forced to conclude that it was the whole space again. All right. I think that the image can't be empty because of the setup here. I don't know. Maybe there's a trivial case to think about. Sorry. I'm going to go on. Okay. So proof 2. Here's a proof 2. I mean, I like the proof above. It's okay, but I kind of like my proof 2. Suppose the f of x is the union of a and b, with a and b non-empty disjoint, a and b open in f of x. Then there exists. So what I'm trying to do is to show that I want to show that this doesn't happen. So this is a proof by contradiction. I'm going to assume that assume the image is disconnected and see how it breaks down, yeah? So if f of x is the union of a and b with a and b non-empty, disjoint open sets, then that means that there exists VA and VB open in Y such that the intersection of, f of x with VA and f of x with VB gives us back A and B respectively, right? And those are both open. But then the inverse image of A union B is the inverse image of A union the inverse image of B, which is respectively the same as the inverse image of VA and the inverse image of VB. Again, it's that same set theory idea right there. But lo and behold, that's a separation of X, because if A and B are non-empty and disjoint, then that implies that these are also non-empty and disjoint, which is a problem, because that would give us a separation of X, and that contradicts the connectedness of X. Anyway, so whatever proof you like, I'm going to go on here. Main takeaway there was that the continuous image of a connected space is connected. All right, so page 6. I'm getting there. Definition. A topological space is path connected if all pairs of points, x, y, in the space, there exists a continuous map, let's say alpha, from the closed interval 0 to 1 to x, for which alpha of 0 is x, and alpha of y is 1. Such an alpha is called a path from x to y. All right, so here's an example. If you look at Rn with the Euclidean topology, you can see it's path connected. If you pick a point P and a point Q and X, you can form the path alpha of T, P plus Q minus P times T. Alpha of 0 is clearly P. Alpha of 1 is clearly Q, because we get P plus Q minus P. We put in T equal to 1. And this formula is continuous in the Euclidean topology. So that's a path. And, well, by the way, this is just the standard how do you parameterize a line between 2 points in calculus 3 trick anyway. Okay, so anyway, there you go, proof. Rn with Euclidean topology is path connected. What else do we got here? So this is a little bit cluttered. I didn't need to quite write so much, but let me just kind of sort through it here with you guys. Let V be a finite dimensional vector space over the reals for which the coordinate map, phi beta, is a mapping from the vector space to Rn. All right, and suppose that that coordinate map is continuous with respect to the topology given to the vector space. All right, so here beta is the basis, and here's the coordinate map. It converts this abstract basis to the standard basis, and then you extend linearly. That's how we define it. And then if you pick x and y in the vector space, then you can of course expand x into its coordinates and y into its coordinates. And so I get like the coordinate vector of x with respect to beta is that, the coordinate vector of y with respect to beta is that. And then I was thinking I could use these to form this formula down here, like phi inverse of beta of x plus t times phi beta inverse of y minus x, and then my thought was like that would give me a path. And if I know that the coordinate maps and their inverses are continuous, then this is a continuous map, so it's continuous. And that's all true, but there's a much easier way to think about this, which I thought of after I wrote all this, so forgive me for not erasing it. You could erase it if you want, all right? But there's a simpler argument here, which is that this is the path from x to y in the vector space. And it's clear that the image is in the vector space, because if we take a sum of a vector and the scalar multiple of a difference between vectors, well, that's still a vector, and the vector space is closed under such things. And so all I really need in terms of topology from the vector space, I need that the addition and the scalar multiplication and, okay, fine, the subtraction of the vector space. If those are all continuous operations with respect to the topology of the vector space, then this is a path. Yeah? So, and pretty much any finite dimensional vector space, if you look at the topology of it, you can prove that vector addition and scalar multiplication are continuous, and hence any finite dimensional vector space is going to be path connected, because okay, come on. Any finite dimensional vector space is really just Rn in disguise anyway, right? All right, so there's a couple of examples. That vector space example is not in Minetti. That's just me, because I like to talk about vector spaces. You know I am. All right, so now let's circle back. Circle back here to path connected versus connected. Any path connected space is connected. Ooh, interesting. All right, so suppose X is path connected, and pick A and B open subsets of X such that their intersection is non-trivial, and their union is all of X. We seek to show that, excuse me, I don't say that intersection is non-trivial. I suppose that they're non-empty sets whose union is X. I need to show that they intersect somewhere. If I can show that necessarily for any arbitrary pair here of open subsets whose union gives the whole thing, then that would prove that there doesn't exist a separation of X, and hence that X is connected. Okay, so let's get to it then. X is an element of A, Y is an element of B. We can pick a path that starts at X and goes to Y. We can do that because we're assuming the space is path connected. And then, scroll down here a bit, we have, so here's kind of my silly picture of it. I guess I forgot the label, but I was thinking of the, oh man, well, I'll just keep going on here. So I was thinking of A as being this one and B as being that one, and I was using the red to be like the A set, and B to be the blue set. Okay, and then here's my path going from X to Y, and all right. So look at it then. What do we got? The inverse image of A. Right, inverse image of A under the path map, that's going to give me basically like this part, all right? But the point is that since this is a continuous map, the inverse image of this open set is open. So that right there is open, right? Let me use this. So you think of this right here. There's your alpha inverse of A, all right? And likewise, alpha inverse of B is this part here, right? But the larger point is that both alpha inverse of A and alpha inverse of B, they're open subsets of, oh my bad, I'm an idiot. That's the wrong place to picture it. That's the image. This is the, oh good grief. That's not the right way to say it. Let me erase. My bad. The inverse image of A maps to the thing I just shaded. All right, but the inverse image of A under alpha is a subset of the, 0 to 1. I technically should draw like another picture over here. Picture over here. Here's my, 0 to 1, and alpha maps like that, right? And so the inverse image of the path of if I take the inverse image of A, right? The inverse image of most of the points in A are empty because it's not the path, But the inverse image of the part of A, which is the path, that's going to give me some kind of like, open subset over here, which would look something like that. And then the inverse image of B would give me something that is like this, like that. And so the thing is then that since A union B covers everything, that means that the inverse image of A union the inverse image of B under alpha, it has to be everything. Because the inverse image of the union of the inverse images is the inverse image of the union. Did I have it down here? Curses. I should probably write that somewhere. So like alpha inverse of A union alpha inverse of B equals alpha inverse of A union B. But A union B is X, right? It's everything. And as such, that has to give us the whole domain of the path, which is what I claimed right here. Anyway, that's the internal logic to that equality right there. And so, okay, that means that these are open sets whose union gives you all of that, but we proved that 0, 1 is connected, right? So since 0, 1 is connected, that means that these must not be disjoint, because if they were, they would separate 0, 1, which would prove 0, 1 is disconnected, but it's not by real analysis. And consequently, we find that there exists a z that's in the inverse image of A and the inverse image of B, and as such, alpha of z is an element of A and B, which means that alpha of z is an element of the intersection, which means that my open sets A and B do not form a separation, because they are necessarily intersecting. And at this point, we realize the problem with my easy proof of 0, 1 being path connected. So the problem with my second proof on page 4 is what? It's ultimately circular in view of how you have to prove the theorem path connected implies connected, right? So because the nuts and bolts of the proof path connected implies connected it's anchored on the observation that 0, 1 is connected. So you can't really very well use this theorem to prove that 0, 1 is connected unless you believe in circular logic, and I guess if you want to, I mean, it is very symmetric, but usually discouraged. So anyway, that's why we should use the first and uglier real analysis proof, because we want a proof of 0, 1 is connected, which stands on its own, all right? Anyway, the converse of the theorem, path connected implies connected, is generally false. However, open and connected subsets of Rn are necessarily path connected. That's actually proposition 10.5 in Minetti. The usual example of a space which is connected but not path connected is the topologist sine curve. So it's something like this, like that, and then like that, and then like wee. And then you like union it with the vertical line segment, I think, from like -1 to 1. And so you can prove that that monstrosity is connected, but it's not path connected. If it's not obvious to you, well, good, it's not obvious to me either. But this is one of those, like, get some coffee and a donut and take your time kind of exercises. It's essentially exercise 4.20 in Minetti if you want to try to work on it. But I think that proving that this is not path connected is probably harder than anything I'm doing in this lecture, if I had to guess. Anyway, let's move on here. So let A and B be path-connected subspaces of X. If A and B meet, if they're non-empty intersection, then A union B is path-connected. So if you've got two path-connected spaces, you can put them together and get another path-connected space, provided they meet somewhere. And so the proof is really fun. You take 2 points, right, in the union. Well, of course, if both points are in A, or if both points are in B, then by assumption there's a path that connects X to Y, right? So that's not interesting. So what we need to look at is when X, without loss of generality, because X and Y appear symmetrically here, right? And as A and B as well. So let's put X in A and Y in B, and let's figure out how to get a path from X to Y. Now, we know that we need to use that intersection point somehow, so let's let Z be the point in the intersection, which we're assuming exists at least one point, right? And since A and B are path connected, there exist paths alpha 1 from X to Z, and alpha 2 from Z to Y, right? And so then you just construct the join of these two paths. You do the first one at double speed, and then you do the second one at double speed. And so, like, in other words, just like time 0 to 1/2 gets you from X to Z, and then time 1/2 to 1 gets you from Z to Y. And you can check this. Alpha of 0 is alpha 1 of 0, which is X. Alpha of 1 is alpha 2 of 2 times 1 minus 1, which is alpha 2 of 1, which is Y. And they meet in the middle, because if you look at, I could put equals just on one and the other, I put it on both, just to emphasize that they both match up there. So there's something called the gluing lemma, which proves that if you have two continuous maps which agree on a restriction, then if we glue two maps together like this, then it's again a continuous map. So we know alpha 1 and alpha 2 are continuous because of the path connectedness of A and B respectively. Lo and behold, we have a path from X to Y, and we've proved that the union of two path connected space is indeed path connected. All right, so here's an example. Example 5, he wants to look at the n-sphere, right? So the n-sphere is the set of points in Rn plus 1 such that they have length 1 in the Euclidean norm. And he argues that this is homeomorphic to the union of Rn and Rn. And how does he argue that? Well, he says by the stereographic projection. And okay, basically you can look at almost the whole sphere, like the sphere with the north pole deleted as Rn. You're looking at the sphere with the south pole deleted. It's also homeomorphic to Rn. The mapping is roughly this. So like I can draw it in 2 dimensions. You take the north pole and you map to the real line in green down here. This is the stereographic projection like that, right? So we're projecting this point right here to that. Here we're mapping this point to there. We're mapping this point to there. We're mapping this point to there, this point to there, this point to there under the stereographic projection on the sphere with the north pole deleted. See, the north pole doesn't get mapped to anywhere. It's just used to define the mapping on the north pole deleted sphere. Of course, in that case, the south pole it gets mapped just right to there. Okay. So we can use a stereographic projection to map the north pole deleted sphere to the green line, and we can also use the south pole deleted sphere to map the south pole deleted sphere to the red line. So like this point maps to here, this goes to here, this goes to here, this goes to here, this goes to there, this goes to there. And I'm just drawing it as a 2-dimensional picture, but the concept generalizes to n dimensions. The formulas are given in a different section of Minetti, right? And you can prove that these mappings that I'm describing here, which is so-called stereographic projection, that these are in fact they're bijections, and they are in fact continuous, with continuous inverse with respect to the topologies in play here. And as such, we get that, well, notice that the sphere is the union of the north pole deleted sphere and the south pole deleted sphere, and since their intersection is everything but the north and south pole, and that's of course not empty, right? And what else? Well, we proved that Rn is path connected, and homeomorphism preserves path connectedness. I'm claiming that. I haven't proved it, I suppose, but that's something you could prove. We find that the sphere with the north pole deleted and the sphere with the south pole deleted are path connected, and hence Sn is path connected, right? Because we can look at the n-sphere as the union of the deleted north sphere and the deleted south sphere. Those are both separately path connected, and they intersect non-trivially. In fact, they intersect at a lot more than a point. They intersect everywhere except for the north and the south pole. Very greedy. And there you go. That gives you proof that the n-sphere is path connected. So that's pretty slick because it works it's an n-dimensional proof. That's kind of neat. It's kind of neat. I was like, I can be more concrete. And then I realized, well, yeah, I can, but my concrete proof really only works for dimension, well, the 2-sphere, yeah, which is embedded in 3 dimensions. So here's how you could prove like the 2-sphere, S2, is path connected. What I would do is I would just, parameterize the 2-sphere with the usual spherical coordinate map. And then if you pick 2 points on the sphere, then you can find corresponding parameters that map to those points. And so obviously there's a line in parameter space which maps from the 0.1 parameters to the 0.2 parameters, and then you can just lift that path through the spherical coordinate map to get a path up on the sphere. And that's how I would prove path connectedness of the sphere. But that's a concrete proof of how you prove. If you've got a parameterization of your space, you can probably prove. You might be able to lift path connectedness in the in Rn in the parameter space for that space up to the up to the manifold in general, I suppose. But anyway, I move on. I think a lot of times we assume the manifolds are connected, but well, not always, I suppose. I guess we'll get more into that next section. Next section's on path components, which of course is interesting. I'm not sure I'm going to make it under an hour for this lecture. No! I hate making 2 videos. I feel like this may be part 1. So suppose A, a subset of Rn, is convex. Alright, I'm calling it. It's going to take more than an hour. I'm going to stop and start here.